Hi, welcome. Today we're going to be looking at how to run a hypothesis test using z-scores. The example we're going to be using is as follows. The researcher suspects that special training in reading skills will produce a change in the test scores. For this, we're going to assume that we have a population with a mean of 65 in terms of this test with a standard deviation of 15. If we select a sample of 25 individuals and we give the treatment to this sample, we get the following sample mean of 70. So the question is there evidence that the special training program that we have, has an impact on test scores? So the first thing, let's look at this another way, so that we're going to ask this question. After the training, if we gave the training to the population, would it significantly change the mean? Now notice here we're not talking about increasing or decreasing, although we may intuitively want to do a one-tailed test here. We're just going to see if there's a change. So our first step in doing our hypothesis test is we need to state our hypotheses. So here, let's review the question again. The question is there evidence that the training has an impact on test scores? It's an alpha level of 0.05. So we've decided to set our alpha level at 0.05 here. So for our alternative hypothesis, we're going to say that mu, or the population mean, is equal to 65. Basically saying there is no impact. It did not significantly increase or decrease an individual's test score. Our alternative hypothesis is that it's not equal to 65. Mu is not equal to 65. This is kind of what we're going for. Now remember, we're always talking about in terms of the null. We're either going to reject the null or fail to reject the null. So let's think for a second, what does that mean by rejecting the null hypothesis? So if we take a look here, what we're saying here is we're saying that the mu is not 65. Now we know that any sample mean is likely not to be exactly the same as the population mean, although we do expect it to be close nearby if we have it, if there is no effect. What we're saying here is that if there's no effect, excuse my crude bell curve, then we would really expect the sample mean, to fall somewhere within here, really close to the mean. But how close? When do we know? What's the level of certainty that we want that we have actually selected the sample mean we have is significantly different from our population mean, right? Because we do expect it to be different from the mean. Well, we figured that out in step 2. Step 2, we set our alpha level. We set the probability that we would, just by sampling error, select a group of individuals that have extreme scores. Now, we've already selected this alpha level to 0.05. This basically tells us we have a 5% chance of committing what's called a type 1 error, or rejecting the null hypothesis when we should in fact have retained it. Now, we also need to know, to figure out what our critical value is we need to know whether we're doing a one or two-tailed test. In this case, we're doing a two-tailed test because we're not looking for a directional hypothesis. We're not saying whether it's going to increase or decrease scores. We're just asking, does it have an impact? Another thing we need to know is we need to figure out our z critical. Now, how we do this is we need to go to our unit normal table. So let's take a second and let's pop over to our unit normal table. Alright, so here we are at the unit normal table. And what we want to do is we want to find, since we're doing a two-tailed test, so we're looking at, we can use this as an example here, we are looking at trying to find the individuals that are in the lower or upper tails. Now we set our alpha level to 0.05, so it means we need to split that probability to 2. So we're looking at what's the z, or what's our critical value, that separates the top 5% and the bottom 5% from the remaining 95%. So what we need to do is we're going to look in the tail for, so half of 0.05 is 0.025. And so if we go down, here we go. And so this is in the tail. Here we go. Here's 0.196, 0.025. And so this is the z-score that separates the top 5% from the bottom 95%. Let me zoom in there for you so you get a better look at that. So here we are. Now if we were doing a one-tailed test, we wouldn't have to split it. And we would simply go and find 0.05. And we get the closest we could without going over. And this would be our alpha level. But since we're looking at a one-tailed test, our alpha level is going to be 1.96. Alright, so here we are. Now that we know our z critical value is 1.96, we can plot it on our curve, which is going to help us keep from making mistakes. So let me pull out my pen here. Now, one thing we should notice here is that since it's a two-tailed test, it isn't just 1.96, it's plus or minus 1.96. We are looking at either side of the curve. So we're interested in whether our z observed falls in here, in these locations on the curve. Okay. So these are the three things that we're looking for here when we are kind of thinking about where our critical value is. What our alpha level is, what kind of test we're running, as well as what our z critical values are. Alright. So after we know what our hypotheses are and how we're going to evaluate those hypotheses, that's what we do in step 2, is we're determining how we're going to evaluate those hypotheses. Next, we need to do the math. Now, the math here is just doing a simple z. And so we have to first compute our standard error. And remember, sample size really impacts our standard error. And so as our sample size gets larger, our standard error is going to get smaller because we're going to expect less variability around our distribution of sample means. Now, if you look over here, all we do is we put the standard error down here. We're looking at our mean difference. So this is the mean, this is our sample mean, this is our population mean. And we get a z observed of 1.67, which is important. So we need to mentally keep that in our heads, a positive 1.67. So the first thing we can know here is, since obviously we have a positive sign, that the difference is the sample mean is above the mean, which is what we were kind of hoping for, but of course we're doing a two-tailed test, we didn't hypothesize that. And we know that it is about a little over 1.5 standard deviations above the mean. That's what the z-score tells us. So let's go move on to our next slide. So after we do our math, we need to ask our question: do we reject or do we fail to reject the null hypothesis? Remember, these are the only two options when we are looking at this, because we never can accept the alternative or reject the alternative hypothesis. Now, I'm not going to go into the details on why that is, but there's plenty of videos on YouTube as well as the books on this subject that we can look at. So, but these are our two options, and let's kind of go back. Let's think again. What does that mean? We reject the null hypothesis. Our null hypothesis again was mu equals 65. And basically what we're saying here is that our training did not impact test scores at all. So if we reject that, we're basically saying, we have evidence that suggests that our training does impact test scores. If we fail to reject the null hypothesis, we're basically saying, we're not saying the null hypothesis is true, But we are saying that we don't have evidence to reject the null hypothesis. We fail to reject the null hypothesis. What often helps is if we take our z observed and we put it on a graph with our z crits. So let's do that. So if we do that, we see right here, so this is our 0 point. We place our 1.67 right here. And we can clearly see that our observed value does not fall in our critical region. Because it does not fall in our critical region, we fail to reject the null hypothesis. Or we are basically saying here that our treatment did not have an effect on test scores. Now, one thing that affects this is what kind of test we use. So for example, if we decided to use a one-tailed test here and we hypothesized that it was going to increase test scores, our critical value, of course our critical value here really honestly should be right here, shouldn't it? Because that's 1. So really, this should be right here, so 1.67. It's a little typo for you. If we decided to do a one-tailed test, we would have a z critical of 1.65. And we would have the opposite conclusion here. We could conclude that our results did significantly impact. That's why in step 2 it's very careful that we use the right kind of hypothesis test. Alright. So now that we have our results, now that we are going to fail to reject the null hypothesis, we need to interpret that, because up till now, I mean, there's nothing in here. If we go back to step 1, if we ignore everything that's happening up here, doesn't really reference the actual question, right? So here this is just basically, is the mean greater than 65? If we were just to look at this, just look at step 1 without the question, we wouldn't have any context of what we're doing here. So we could easily, if I could just gave you the numbers without any context, you could create a hypothesis, you could set your critical values, you could compute z observed, you could reject or fail to reject. But what separates what we're doing here from what we've been doing, or what you're doing before hypothesis testing, is that now we're not going to interpret it. Now interpreting it can be tricky. So let's look at some of the elements that we need. So here's a good one-sentence way to summarize our results. The results suggest that the special training in reading did not significantly impact test scores, with a z of 1.67, p less than 0.05, with a two-tailed test. It's important that we have all those elements in there in order for us to correctly kind of convey what our test was looking at. First, let's look at our independent variable. So it's very important that we have our independent variable and our dependent variable in here. The reason for that is it gives context to going back to the original question. The original question here is, what impact did special training in reading have on test scores? So here is our special training in reading. So this is our independent variable. And test scores, dependent variable. This is what we were looking for changes in. Now we also needed to determine whether it was or was not significant. So here we clearly state it did not significantly impact. We'll get to that in a second, right? Next, we need to look at the direction. Did we have a direction hypothesis? Did we not have a directional hypothesis? If we did not have a directional hypothesis, we can simply say it impacted test scores. We can say that it affected test scores. If, however, we hypothesize that it increased test scores or decreased test scores, we will need to put that in there because, again, it's providing the context of what we expected to find. Finally, following APA guidelines, we need to report our statistics. The reason why we need to do this is that other people coming after us need to look at our results and be able to say, oh, okay, I understand what they were doing here. So what we have here is we have our z observed, comma, our p-value that we use for our alpha level. Now I want to clarify this. is always going to be p is less than 0.05, or whatever your alpha level is, for the work that we do by hand. The reason for that is that we don't know the exact probability of 1.67. Or we may be able to find that probability, but a lot of times we don't. A lot of times we don't know what that probability is. And so all we need to know here is that we set our alpha level at 0.05. We also need to know what kind of test we ran. If we ran a 1 or 2 tailed test, as we kind of discussed in step 4, it impacts what our results, how we interpret the results of our test. One final thing that we need to think about is effect size. Now, effect size is just our mean difference over our standard deviation. Very similar to our z-score formula that we used before when we were looking at individual raw scores. But here, we are going to take the sample mean over minus the population mean and divide it by our standard deviation. Remember, in our standard error, the sample size decreased the standard error we're going to expect. This is a way for us to look at what is the absolute magnitude of the effect the treatment had on the overall population. And we can interpret this in terms of standard deviation units. For here we can say that the treatment would cause a shift in the population by 0.3333. So this would be a small effect size. Now, typically, if there was results were not significant, we would not look at effect sizes. In this case, we wouldn't. But let's say, for example, that we did want to look at effect sizes. How would we report it? Is we report it by just putting it here right after our two-tailed test. So we'd report our statistics, and we would give our Cohen's d. So d equals 0.333. This is important. You wouldn't underline it, but this is important because it's going to give us context. It's going to say, what is the effect size controlling for the size of our sample? Because you can have hundreds and hundreds of people and get something that's significant, but that does not have a substantial impact. All right, well, that wraps things up. If you have any questions, you can refer to the handout that was given to you in class. Have a good one.